So let's do a quick review of some of the topics from the last set of lectures. And one of the main topics dealt with what the mole was and using Avogadro's number. Let's take a look at a typical Avogadro's number style problem. The average size of one copper atom is 140 picometers. If you were to lay a line of copper atoms end to end, how many grams of copper would you need to stretch 1 kilometer? A very typical Avogadro's number style problem, talking about individual atoms. So we take a bunch of coppers, and we end up stretching them 1 kilometer. And so this is just a dimensional analysis problem. So we have to think about how this lays out. We have this bunch of copper, we have to stretch them 1 kilometer, and we're told how big one of the coppers is, and we want to know what the total mass is. How many grams of copper could we get away with to do this? So we need 1 kilometer of copper. Well, that's a distance, so we have to convert our distance into something we can use, and it turns out that we can relate that to numbers of atoms. And of course, we now know using Avogadro's number, we can convert numbers of atoms into grams. So probably a more direct would be to convert our 1 kilometer into something usable like meters, and then into picometers. And then from there, we can relate picometers to atoms, because 140 picometers is equal to 1 atom. And then we can go from there, atoms to grams. So I will let you set that up. So we can set this up as follows. We can use our conversion. The fact that 1 kilometer is equal to 10 to the 3rd meters. The fact that 1 picometer is equal to, again, this is just metric conversions. This particular conversion factor comes straight from our problem. And this is the definition of Avogadro's number. And lastly, this is our definition of molecular weight. All individual bits of information that we know, allowing us to calculate the value. So we get as a value 6.53 times 10 to the minus 10th grams. So basically nothing, almost nothing. You know, a speck, a microgram is 10,000 times as big as that. So the sheer number of atoms in something is quite astronomical. So that's a typical Avogadro's problem. And again, the trick is to look for the word atom. Well, let's take another look at Avogadro's number. Using Avogadro's number, we'll introduce a new concept, and we'll talk about it more over the course of the next few lectures, and that is this idea of concentration, which is a value that relates a volume to a molecular quantity or an amount, right, such as grams or moles. Concentration is a way of expressing how much material is present in a liquid, or how much material is present in a solution. So we typically measure out volumes of solutions. With liquids, it's much easier to do than to deal with masses. So we introduce this quantity of concentration. And one typical concentration is the ppm, the parts per million. Probably one you're familiar with, or its little brother, parts per billion. These two quantities are used for representing milligrams per liter, or micrograms per liter. In reality, they're actually derived from the mass of solution. Turns out that, because of the fact that water weighs about a gram per milliliter, you could, for dilute solution, express this as milligrams per kilogram, or micrograms per kilogram of solution, water in this case. And if you have an eye, you'll see that, well, milligrams are 0.001 grams, and kilograms are 1,000 grams. And so if this was in the same units, this would be 1 per 10 to the 6th. 1 gram out of 10 to the 6 grams, or 1 part per million. So pretty slick how that works. You can do similar calculations for micrograms and get exactly the same thing. So you can think of these as representing small quantities. When I use them, I like to think of them, express them in this fashion: a milligram per kilogram. So a 60 parts per million solution would represent 60 milligrams in a kilogram of water, 60 milligrams in a liter of water. Now this liter-kilogram relationship only works for very, very dilute solutions. So it's a fudge. So parts per million and parts per billion are working under the assumption that the density of the solution is relatively constant. So let's take a look at a typical problem where it glues itself onto a Avogadro's number problem. It turns out that MTBE, methyl tertiary ether, is a fuel additive used to oxygenate gas. And it's known to give water an odd taste at about the 20 part per million range. So the question is, in a 300 milliliter sample of contaminated water that has a 20 part per million concentration, how many molecules of MTBE are present? So if we take our 20 parts per million, 20 parts per million, again, is a conversion factor. It relates milligrams, 20 milligrams of methyl tertiary butyl ether, which happens to have a molecular weight equal to 88.1 AMU. So it relates the 20 milligrams that is equivalent to 1 liter of solution, water in this case. So our thought process for this would be to take our volume in milliliters, convert it into liters, then from there convert our liters into milligrams of MTBE, which we can then convert into grams of MTBE, which we can then convert into moles of MTBE, and then we can relate moles to the number of molecules using Avogadro's number. This would be the molecular weight, and then this would just be our metric system. Again, set that up, run through the calculation. So, even though we're still talking about 1 part per million, 1 in a million, or in this case 20 in a million milligrams per kilogram of water, we are still talking about an astronomically large number of molecules. What makes a mole is deals with this very large number of molecules. So start to be prepared for units that relate volumes to masses in moles, typically volume in moles. And then we also talked about limiting reagent problems. When we deal with limiting reagent problems, almost always these problems have 2 reagents, and we are asked to determine information about them. So if you start with 3.00 grams of CH4 and 2.5 grams of O2, first question asks, what's the theoretical yield of CO2? Usually expressed in grams. Now there's two ways to do this. I'm only going to show one, and that involves converting each of these to the products, though I personally prefer the alternate method in the last episode of this lecture. Take our grams of CH4 and we convert it into our grams of CO2. Theoretically, that can be made assuming there is enough of all of the reagents. I'll let you set that one up. 8.23 grams of CO2 can be made only considering the CH4. And then if we do the same thing for the O2, for the 2.5 grams of O2, so taking into account just the O2, we can see that we only make 1.15 grams of CH4. This means that the O2 is the limiting reagent. Then we can use that as our starting point. So the theoretical yield, the maximum we can make, is 1.15 grams of CO2. Now the other half of the question asks, how many grams of excess reagent are left over at the end of the reaction? Well, the excess reagent is the CH4. So the real question is not how much is left over, but is how much is consumed. And so we always start with the limiting reagent. So we start with the limiting reagent, 2.5 grams of O2, and we ask ourselves how many grams of CH4 are consumed. And so if you run through the calculations, you find that much oxygen only allows you to consume 4.184 grams of CH4. So if we take the CH4 we start with, we subtract out the CH4 we used, that will be the excess. So in this case, it would be 3. So it's very easy to predict what your excess reagent is.